So then welcome to apparently the sixth lecture in parallel and distributed computing, if the counting is now correct. And today we'll talk a bit about one problem that last time we got in the exercise, where you remember we were computing the number of primes in an interval, and the number of primes, they become sparser and sparser. One thing, they become sparser, and the larger the number is, and also it becomes more and more difficult to compute them. So it is not intrinsically obvious how you distribute this kind of work between the different parallel entities. Yeah? And this is something that we observe very often, and the solution is usually depending on the problem. But the general question that has no exact answer, no answer independent of the problem, of course, is how to divide the work between workers. Okay, now work can of course be divided in different ways. So, for example, in our human, the way we divide work between different humans is usually you can do this best, so you do this, yeah. And so, for example, Mr. Kutsche knows about everything about the cluster, yeah. So he is talking about the cluster and the implementation stuff here, and I may be a bit more deeper in theory, so I'm standing here and give you the theory, okay? So all the time we divided who can things do best. But in the computer, we assume they are all the same, and we have a list of items, of work items that are generally similar, and now we want to divide them. Yeah, so this is our starting point. Of course, there's also the case where you have different things to do, yeah, which also can be done in parallel. But this is much harder. So the starting point, our starting point is that we have a list, a sequential list. So we start from a sequential program, saying that in principle we could do this, we could do all of this in our spaghetti code. So a sequential program that is processing multiple independent, that's important, otherwise we cannot easily split them up, independent work items of the same kind. So what do I mean by the same kind? So the same kind usually would be something that you can do in a loop. Yeah, they don't need to be exactly executed. They don't, in the end, it is not required that they do exactly the same thing, because they can be conditional, yeah, but they run the same program. Yeah, there's the same algorithm to input, and depending on their data, they may do different things. So, for example, seeing we have a loop, we put these things in a loop where we can work sequentially. Say, no, 0 is stupid. Say 1 is okay. Let's start from 0. So we have an index I starting from 0, and this must be smaller than n, and this we count up, and then we do work. So then the work that has to be done is identified by the index I. Yeah? So this is a very simple example. So this is our starting point. So if we have a problem of this kind, yeah, so how would we distribute this? And the way we could distribute it is cutting this this list of items that we have to do the work items into different parts. And the question now, of course, is how to do this. And when this works, so the most basic idea is just to cut it in parts, and this is what we call static loop scheduling. So a fancy word, because there's also non-static, yeah, dynamic. So what would this mean? You have a subset. So each worker gets a subset of the work items, right? That's pretty simple. Subset of work items are assigned to each process. They should be non-overlapping usually, so each one gets their own, which the others don't get. And the subset that is assigned to a worker does not depend on the output of the work. Which means, without the work having been done, it is decided who does what, right? So if you do it like this, then there is no way back if some part of the work turns out to be much more difficult than other part of the work, right? So you get, so in the beginning, we want to build a skyscraper, and there are 1,000 workers, and each one of them gets their task, and though they start working. One gets into trouble, yeah, struggles hard. Another one sees, okay, so there's actually nothing to do on this floor, so I'm done, yeah. So and I can go home, yeah. So there's no reassignment of work later. What did I want to? So it means there's a predefined set of tasks. So how did we solve? Can anybody remind me how did we solve the division of the work with the prime example last time?
We divided the outer loop, and then we used one, I think it was reduce.
Yeah. Okay. No. Yeah. This is how we combined that. Okay. So this is what how we combined the result. But how did we distribute the work?
We tried to do it equally, right?
Okay. Anybody remembers how we did this? Equally. So what is the problem with? So you mean what you mean with this? Gesture.
The for loop had one. The rank or
Yeah.
the rank and the size was involved in the loop.
It was involved in the loop, but in what way?
By the steps.
By the steps, right. So, okay, why did we, is this the only possibility how we could divide work?
I guess not. There could be more ways. Maybe.
yeah, I mean, this is probably not even the most obvious way how to do it. I guess usually the obvious way how to distribute something is to take, okay, I have here, you know, say I have these boxes with bottles, yeah, and now I could, and I say I have three boxes with bottles, and I want to distribute them to 3 people. So one way to do this is give each person a box with the bottles. This is not what we did. So we picked one bottle from one box, and the first bottle from the first box gave it to the first person. No, the first bottle of each box and gave this to the first person, then the second bottle of each box and gave this to the second person, and then the third bottle of each box and gave it to the, and so on, yeah? So this is how we decided. So it would be more, maybe it would be more natural if you have 3 boxes that you just give or if it's just one box, yeah, so you would take the first 3 of them, give them to one, and the next 3 of them, give them to the other, yeah? So why did we, what was the reason why we didn't get a chunk of numbers, but each P of numbers? What was the reason for this?
Because the steps were different in each iteration, right? Or the number of primes that we get.
Yeah. So the problem that would arise here is that for the larger numbers, calculating whether they are prime is hard, while for the smaller numbers, it is comparatively easy. So if you would cut it like this, just the first 100 to the first process, the next 100 to the second process, the first process would have a much easier task than the last process. Yeah. So this is, but this is of course now a problem that arises specifically in this example. Yeah. So we can, and what we did is exactly this. We did static loop scheduling, yeah, because we had an idea. We know our problem. Yeah, we were not naive. If you let a computer decide, I mean, or if you are naive and you don't know how expensive it is to compute a prime, then they would simply cut it in the same pieces. Yeah? And the problem is if you use any automatic software to split up your problem, it would be naive to the problem it is supposed to solve. So it does not know this. So the natural way of doing it, it would just hand the same number of tasks to every, maybe, yeah, the same number of tasks to each process. So this may has problems, but it also has advantages, namely that no master process is required. Now I have to specify this a little bit. In fact, we use the master process. Why did we use a master process? For computing the primes? What did the master process do? Well, it did the output. We wanted to have only one output. So the master process was required for the output. But the master process was not required for deciding how the work is distributed, because each of the processes could calculate their own chunk of work. Yeah? Because the equation that we needed to compute its own chunk of work was pretty simple, so that they could decide this on their own. And this is a big advantage of this static loop scheduling. So its own set of assignments. So basically, all we need is we need to know our rank, and from the rank we can compute what part of the problem we are supposed to solve. If we use static loop scheduling. Okay, example. So say we parallelize the outer loop, which I indicate by just saying for parallel. So this outer part would now run in parallel. So there's an integer j equals to 0, and j would be smaller than the number of processes. Processes, probably. And then we count this one upwards. And then we have another loop. So this is now this here is parallelized, and the inner loop is still run as a usual sequential loop. Yeah. Now we have to compute just the starting index from the number of processes, of work items that we want to process, divided by the number of processes. So this would usually be an integer operation, so it's rounded down, and I must be smaller than j plus 1 n divided by num process. And we are counting upward, and then we do work, and we close our brackets. So this is how we would do it. Yeah. So by the way, there was last time the question: do we split the inner loop or do we split the outer loop? Yeah. So here it's very clear we split the outer loop, but this is not the only possibility. We'll come to another possibility in a minute. So this way of cutting things up may be a good idea if the execution time of do work of I is the same for all I, which in reality usually is not the case, or very often is not the case. This way of cutting things up has a name. So this distributing supposed to be a U this here. Distributing consecutive chunks of work item. Consecutive, my dyslexia. This is called blocking. So basically we take a block of operations is usually associated also with a block of data in memory. Yeah, because the operations usually depend on data. Not always, but most of the time. So say we have a data dependency. So here we have our chunk of data. That's all of the data, and then there is a data block 1. Data block 2. And the data block 3. So and now it makes sense that worker 1 would work here, worker 2 would work here, worker 3 would work here. So now this is different from what we had with the pi. The pi example was a little bit specific in that sense that it was not depending on data. Yeah? So it was something that was intrinsic to the number that we were, analyzing, yeah? And it did not depend on any data. But usually we have, especially in scientific computing, if we do, for example, finite element analysis, then there is each operation that we are supposed to do is somehow dependent on the data in a specific location. Yeah? And if we are depending on data, there are two aspects that we should take into consideration. The first is that our computers have caches, and they like to read chunks of memory that are they usually read chunks of memory and not just single numbers. Yeah. So if we have to process chunks of data, it is also useful to read them together. Yeah. So this will reduce cache latency and usually not the latency. Sorry, it will reduce the waiting time for the cache. This is one thing, and the other thing is that if you think about, I'll draw a picture on this in a minute. Yeah, if your work is not only dependent on local data, but may also be dependent on neighboring data. So that operations will depend not on several data items, and they would be closer together in memory, which is often the case in practice. Okay, I'll draw a picture in a minute about this. So the blocking, so this is what I said. The blocking improves data locality. So it makes good use of cache. And it may be, depending on the nature of your problem, it may be useful to minimize inter-process communication. Yeah, so this is of course not always the case, but in scientific computing we usually have some sort of data locality. Some sort of, not always and not perfectly. data locality in scientific computing. So what scientific computing often does is solving partial differential equation. So all these finite elements, control volume, finite difference stuff, all what they do is they are solving some sort of partial differential equations. Sometimes people forget this, that this is their purpose. Yeah, simulation is solving partial differential equations. So, and they, solving partial differential equations, operations often depend on their neighborhood. So, of course, the picture, if you think about your homework in particular, so you'll have a domain. In our homework, it is a two-dimensional domain, yeah? And the way data is stored here is, for example, like this. So we'll go over here. So data in a computer is always stored in a one-dimensional fashion in the end, right? Yeah, but so it is always have to unwrap it, if you will. But say you are a cell here. So the next value in this cell depends on the values in these outer cells. Now, locality here is a little bit complicated. Yeah? If the arrangement actually is like this, so then in memory, so this will be in RAM. This will be in RAM, and there would be, say, okay, we'll have different chunks. And here, somewhere in the middle, I didn't draw it very well. Yeah, somewhere here is the index I, and this index I depends on several of their neighbors, namely the neighbor here. So this here is, say, this is the position x plus 1 and x minus 1, and the data for y minus 1 and okay, let's say this is y plus 1, and this here is, depending on where you put your coordinates, yeah, so this is plus 1, because, okay, so this is the y direction, then it's like this, yes. So, okay, you see, in one of the dimensions, it is directly on the neighbor. It's difficult to read the green. Question? No. Okay, so we have some data locality in this in this region here. And we also have the other way around is also some kind of data locality, but this is a kind of data locality that we cannot exploit very well, yeah, because it is because of the unwrapping of the line, this is further away. Now it turns out that you can arrange these things in such a way, yeah, by wrapping them in a certain way that the locality still, that some locality still remains and that they don't get arbitrarily far away. Yeah. So here, in your example, you notice that we actually are going to cut this into squares, yeah, in order to preserve locality inside one of the processes. So we don't only cut in one way, but we cut in two ways and do a subdivision of these things to increase locality and to minimize communication. Okay, maybe that's very natural, yeah, and all clear. Then, are any questions to this blocking? Then we do something that you probably don't. Yeah, please.
I wanted to understand, when we say that I depends on its neighborhood, what do we mean by depends?
Okay, I itself is just the index. It does not depend on something. So think about your homework where we solve the heat equation. Yeah? So the operation that we are going to do in this homework is that we average over the physical neighbors. So the physical neighbors are not necessarily the neighbors in memory. Yeah? Yeah? So this is, you need the data from the two neighbors in x direction that you have, and you need the data in the two in the neighbors in the y direction. Now, since you can arrange only one of them along the memory, yeah, so you have perfect locality in one direction, and you don't have perfect locality in the other direction. Yeah. So now, how bad? Now the question could also be, how bad is your non-locality in the other direction? So what you can, so if you put everything in one box, so and the box say the box becomes larger and larger and larger, then your neighbors in y direction get further and further and further away. So locality is decreased. So what you could do then is not to store data like this. Maybe you can also, you see, subdivide this thing like this, and then you store the data like this. Actually, this is what we are doing in the homework, right? So so this is compared to the above, this would mean an improved locality in y direction. Right? So they still wouldn't, the neighbors in y direction wouldn't be exactly the neighbors. Yeah, but if you take the blocks if you make these blocks not too large, you may be able to read the entire thing in the cache, and then you can also make use of the locality in y direction. So this is, so blocking does not necessarily only mean in blocking in one dimension, but you can, I guess this is why it's called block, yeah? So you could also have 3 dimensions or even more dimensions, and you cut these blocks out to keep stuff locally. Okay? So then I wanted to come to the next topic, which is the loop tiling. So they are not only blocks, but they are also tiles. And the difference here is that instead of parallelizing the outer loop, we can also parallelize the inner loop. So the outer loop, this is what we call blocking. You can also take the inner loop. Okay, so how does this look like and for what is it good for? So how does it look like? Very simple. So we do the for loop, usual for loop, now starting from 0. J is smaller than n divided by the tile size. So this is the number of elements in a tile. Count this up. Here's the loop. And then we do the parallel inside the other loop. So if we do a for parallel int I is to j times the tile size, and I must be smaller than j plus 1 times tile size, and we count up I plus plus, and we do our work. Okay, so this apparently goes against everything that I just said. Can anybody give me a guess what this is used for, and where does it apply? Because some of you suggested that we split up inner loops, and now I tell you, yeah, we can split up inner loops. When do we split up inner loops?
When the number is large.
When which number is large?
For example, when we are solving for the prime numbers, and if the number, for example, it's 20,000 or something, we can.
So why would it then be better to split up the inner loop rather than the outer loop? I mean, I just explained to you why it's good to split up the outer loop. We have blocking, blah, yeah. So why would we split up the inner loop? So this kind of looks. So if you think in the open, not OpenMP, I mean in MPI world, then splitting up the inner loop would be strange, yeah. So because you would distribute the local work everywhere. So you would maximize communication, yeah, and minimize data locality. That's kind of strange. So then from an MPI point of view, this probably is not very useful. But the thing is, we have different ways of parallelization, and we have different machines, right? So the machines MPI is used for as the machines you are sitting in front. Yeah, if you want these two computers to work together in one assignment, yeah, you would use message passing. But what other possibilities of parallelization do we have?
We can use blocking. So, for example, one person does a single assignment and the person another.
Yeah.
Increasing the data they get.
Yeah. So then we do what we did before. Yes. So then we do blocking, and now we want to do tiling. Well, we have single instruction, multiple data. machines, so-called vector machines. Yeah. So what vector machines do is they parallelize the local data. So they get a chunk of data which they process in a vector in one go. And this means they parallelize the inner loop, not the outer loop. Of course, you can combine these two things. You can use MPI on a vector machine, yeah, where you have an outer loop that is parallelized and an inner loop that is parallelized due to vectorization. So because this is a vector operation, it also means that the tiling size is usually fixed. Okay? So again, we have problems with the hardware. I'm very sorry. I don't know why I can unlock this by just using the. Yeah. Okay. So what I just said, the blocking. The blocking is usually used in distributed memory computing. Or distributed memory parallelization. So this is the way we do stuff in MPI. So tiling, on the other hand, is used in vector computation, vector parallelization. In vector parallelization, actually, was kind of very popular in the 90s, probably before you were born, and then it became less popular, and now it became popular again because of machine learning, yeah, and graphics cards. So, what we have here is that the vector size, so the vector size is usually something that is set by your machine, yeah, because your machine has vector register operations. So this just has a size of a vector, and the size of the vector is the tile size, more or less automatically. And this tiling is, because they're always doing the same thing, tiling is always static. Yeah, so they are right. So because you always have to hand in a full vector. And by the way, if part of your vector is empty, you cannot recover these resources for doing anything else. Yeah. So the vector operation always takes the entire vector engine. Okay. Any questions for this?
So, for example, can you, yeah, okay. So that means if the vector size is predefined by the machine,
Yeah.
then let's say we have number 10,000, then it will divide it into that specific number.
Yes.
Okay.
So usually, okay. So what, for example, vectors used to be small, like 16 or something. Nowadays they may have hundreds So it depends on how the machine is built. They usually have multiprocessors, where I'm not quite sure is now what their vector size is, but it is not necessarily a small number. And this means that your work is always divided by this number, and because it's usually not dividable by that number, it means that at the end of the loop, yeah, so there's always some empty spaces that are just wasted, if you will, yeah. Okay, so all of this was we are still in the part of the static scheduling. So static scheduling leads to poor, often leads to poor, can also lead to good, depending on the example, but often leads to a poor load balancing. So load balancing is how much work, or how well the work is distributed over the different work units. So, and this is the case, of course, if, let me see. So I've not read my manuscript, obviously. If the do work of I depends unpredictable on I. So for example, we had the computing the number of primes. This was our example that we had in the exercise in a certain so now, is it predictable? In principle, the number of primes in a certain interval is predictable. Yeah, it is the question whether you can predict it, whether you bother to predict it, or whether your scheduler can predict it. Yeah. So, not predictable means not predictable for the purpose of your implementation. So, because this does not work always, we go to, it's always working, but it's not optimal. So there is, of course, the alternative of dynamic scheduling. Okay, dynamic scheduling. Now this could be anything. Yeah. So the basic idea is, depending on what amount of work you have to do, or whether you run out of work, you get new work. Yeah. So the worker now in our building, the skyscraper, somebody has done his or her assignment and goes back to the master and asks the master, so I've done my work, is there anything else to do? And then the master looks in his papers and says, okay, we still have to do this, now you do this, and then he is making a mark in his paper, okay, now I have assigned this work to somebody. You already noticed the problem. Previously, we didn't need a master. Now we need a master. Yeah. So here we need a master. But the first The first approach would be the worker coming to the master and asking, is there work to be done? And this is called self-scheduling. An idle, I don't know how to write idle. Idle. So an idle worker is requesting work from a master. So that means that the master has to do the bookkeeping. On assigned work. So what does this mean for the execution time of such work? So say we have a parallel execution time TP. This is the number of work items N divided by the parallel workers, which now I call capital P, times B. B is the amount of time that you need, or the average time that you need to do the assigned work, and then there is a dispatch time that depends on the number of parallel workers, and I come to this in a minute. So N here is the number of work items to be distributed. P is the number of processes. B is the average execution time of a work item. And the sigma is a function of P, is the dispatch time. Of the work item. So previously, in the static case, you just get your list of work items that you have to do, and then you don't need to talk to the boss anymore. Now, you run out of work, you go to the boss and ask for more work. Now, this is of course useful if this asking for new work is not expensive compared to the work that you have to do. And this means that B is the work that you're supposed to do, and this is much larger than the dispatch time. I mean, getting new work then is obviously useful. The problem with this is, or the problem can become, is that the bookkeeping of the boss is a serial process. Why is it a serial process?
The rest of the processes are involved in some kind of work.
Can you talk a little bit louder?
The rest of the processes are involved in other work, other assignments.
Yeah, so the others do other things, right? So, but the boss,
Yeah, there is a single process.
there's a single boss. Yeah, why can't we have several bosses?
That would be inefficient.
No, it potentially would be more efficient because more boss can take care of more slaves.
But now you would need to have communication between them.
Yeah, so they have, because, okay, so they may have to make sure, I mean, this we sometimes discover if we, even in a small institute like ours, you sometimes have this problem that something has to be done, yeah, and say there's the secretary and I and somebody else, yeah, tell somebody to do this and that, and in reality some other boss told somebody else already to do this or that, yeah. So now two people are doing the same thing, yeah. So in order to avoid this, there must be only one boss who keeps track of what work has already been dispatched. Yeah? So usually the work of dispatching work is much easier than actually to do the work. This is why bosses can enjoy, lying on the beach, and then it's if the boss can, this is something, I know it's terrible, but as long as the boss can lie on the beach and everything works, this is a good world. Even though you may think this is a bad world, yeah, because one is rich and the slaves are poor. But anyway, when the boss gets into trouble, then all her slaves get into trouble too, right? Then nothing works anymore. So the bookkeeping can be a problem, and we have to look at how this is actually going to behave. So why is this a problem? It's much less work than doing actually the actual work, but if you have many slaves and all the slaves come and ask you, is there any work for me to do? Then you run into trouble. So the dispatch time is expected to grow. So, okay. We could assume that this dispatch time is growing with the number of requests. In particular, the number of parallel. The number of parallel requests. So how many workers you have, yeah? If you have more workers, then more workers come at the same time and asking for more work. Yeah, so you see the behavior, if I may draw a picture, would be like this. Say this here is the number of this is the number of parallel processes doing the work, and this is sigma. So then in the beginning, say there is a dispatch time. This is if your boss is idle lying on the beach, yeah? So there's just a time that you need to go to the boss, ask for work, and the boss hands you in some work, yeah? So, and if, as long as there are few parallel processes that don't step on each other, then there will be no dependency of this time on the number of processes. It will always take the same time because the boss is usually idle. Yeah? Then comes the time when everybody comes into the boss office at the same time. Yeah? And then it takes more time to get the dispatch to dispatch work. So actually you have to wait until all your other slaves, yeah? Sorry for this is the I know we should take this word out, but this is the proper word for the workers in scientific in computer science. There's the slaves. Sorry. Yeah. And they are, they are tough guys. So anyway, yeah. So then this will depend somehow on the number of parallel processes that come into the same time. Yeah, and this will usually be together with a different constant. This is why I call it sigma infinity. So the sigma 0 is the, so to speak, the minimal time if the boss is always idle, and sigma infinity would be the time that if the processes or the workers stand in a line, that it takes to process one of the workers. Yeah, this is not necessarily the same time than sigma 0, but it could be the same time, but it may usually be a larger time than that. Yeah, so and this grows then proportional to p, which means if we take the limit of p going to infinity of what we had in the equation above, which I may just here, n divided by p, yeah. So, and we just look at this part here, so n divided by p times sigma p. So n divided by p times sigma as a function of pi, of p, pi, will now become, because this becomes pi times sigma infinity, so the pi will go away and we have just n times sigma infinity. Yeah? So by the way, this here is the asymptotic. And this here is, as long as the boss is the master is idle, this is what we call pre-asymptotic. So this means in strong scaling, the strong scaling speed up. So the strong scaling was if we have a given size of a system and we want to improve it by having more workers, is limited by the master process. Because the master process has a serial execution. See, this is fun. This is fun stuff, because it actually means that the more slaves the master has, the more work the master has to do, and finally the master becomes the bottleneck of the system. Yeah. So what is how's the speed up defined? Speed up, we call this capital S. The speed up was the serial execution time divided by the parallel execution time. Now the parallel execution time is n times sigma infinity, so this is the asymptotic version, plus nb divided by p. Yeah, so this is the above equation for the parallel execution time. What would be the serial execution time? important question. There are two possible answers. How would you compute the serial execution time? B is the average way, so there are n items. B is the time that it needs to process an item. Then there's a dispatch time, and there's parallel. Okay, no, there's no parallel. Yeah, parallel is 1. P is 1. Yeah. So usually, so what do we usually do if we want to have a serial? If we have an equation for the parallel execution and we want to evaluate this for serial computation. So serial computation is when the number of parallel computers is 1, right? Yeah. So what we can do is we can just up here we can put P to 1. Is this a good idea? Anybody against this?
Well, if we have only one worker, we don't need to dispatch the worker.
We don't need to dispatch, yes. Okay, so we don't need to dispatch. Yep. No need to dispatch. Okay, if we don't need to dispatch, then, see, everything depends somehow on n. So there's n everywhere, so we can divide by n, and we can multiply by p. So I guess this becomes b times p divided by sigma infinity plus b. Yes, I did something wrong. P. Yeah, so, right. Sorry, yeah. So, now, suppose you have infinitely many workers. So this is the limit p going to infinity of s. What you obviously end up with is b divided by sigma infinity. Yeah. So this is your speed up that you can actually obtain from this. So it's basically still the time of work that you have to do divided by the work it takes to actually to get to your work. Yeah. So does this look bad or good or bad? Well, the point is, of course, it's still it is a constant. Yeah. So the speed up is limited. So adding more workers, yeah. I mean, you have to imagine this b divided by sigma infinity is of course a finite number. Yeah, and this is if one worker does everything, yeah. So the maximum amount that you can speed this up is by b divided by sigma infinity for an infinite amount of workers, that is, right? So it may be okay, but it may also not be okay. Okay, for this to improve, what we can do is so-called chunk scheduling. And this is pretty simple. If the worker comes to the office of the boss, the boss thinks, how can we reduce this overhead? So the overhead of the self-scheduling. This can be reduced by assigning chunk of work. Assign So sorry for my dyslexia. Chunks. Okay, what does it mean? Yeah? Now you have many slaves, and since it becomes a little bit hard to hand out one work item at a time, you give them a number of work items at one time, and if you've done all of this, then come back, right? So this simplifies our work a little bit. So we define now a chunk size k, and then the parallel execution time T divided by k becomes n k times p. Now they have to do k times the work, so actually this will be the same as before, yeah. So there's you don't save time on the actual work. The only place where you save time is the sigma, because now the same number of processes come and ask for work less often, namely divided by the number of work items that you attach to them. Yeah. So previously, if you say that each worker gets 10 work items, then they show up at the master's office 10 times less, or times less often. Yeah. And so this picture then changed to this. So there's sigma, there's p, and here's sigma 0. Again, there's a pre-asymptotic part, and then there comes the post-asymptotic part, and this is p divided by k, sigma infinity now. Yeah. So we are able to make this smaller. This also means that the limit of p equal to infinity, n divided by p k sigma p divided by k, actually becomes n sigma infinity divided by k square. And this means I probably have a typo in my notes here. So this TP will now become, let me see, PK. Okay, I think I have it wrong here. Let us think whether this is the correct way of not having it. So n divided by p, and then there must be, okay, I see, kb plus sigma k. Okay, or we could put this, guess we can write it like this. Okay, I hope does this make sense? I think it makes sense, yeah. Okay, now we make this thing here. I hope it makes sense because I have it written down differently. So the speed up in strong scaling S is Ts divided by Tp, is then again n times b divided by n times p b plus sigma. So now my script is no longer correct, so I try to do it ad hoc. So there would be a k square. In this should be k square p b by k square b times p sigma infinity. And if I now made this correct, anyway, it would be the speed up of k square b by sigma infinity, which is different from what I've written here, so I hope it's correct. I mean, there's a big difference. Sorry for this. So asymptotically, it seems to be k squared times faster. Okay, if you discovered that I made a mistake here, then please tell me. Maybe kind of homework, think it through, because it was different in the paper. Okay, anyway, what we see is that the speed up can increase. You can increase the speed up by using here k. This, of course, is only relevant. So for many problems, this would probably not be relevant anyway, because it's only relevant if asymptotically, if sigma n is in the asymptotic limit. This means we have to have enough workers for this to play a role. And this doesn't happen in small problems. By the way, all problems that we are doing here in this course are small problems. So usually, if you don't have a very, very large number of workers, slaves, then the master has enough time to take care of their slaves, yeah, and therefore you'll not go into this asymptotic limit, and therefore this may not be relevant yet, as of yet. But you also know that the ideas of what is a large computer is permanently increasing, yeah, and also what work you can do with a computer is increasing and increasing and increasing, and some things that has been deemed impossible are completely usual here. For example, I think it was probably you discovering that each of this computer here has has a hot IP4 address, yeah, this is nowadays it is probably kind of funny, but the reason why universities can afford this, I mean, this is kind of an asset that we could sell off probably for a lot of money, yeah. But universities were the early ones who needed computer rooms, and they allocated a lot of IP addresses when IP addresses were invented in the 60s, and then the idea was, therefore, we have 4 billion IP4 addresses. So back in the 60s, this was almost twice the number of people alive back then, yeah. And say so that there will never be a time in the future where there are more computers than people, yeah. And this saying when there were much less people than today. I mean, for somebody like me, the population of Earth has doubled in my lifetime. Yeah. So now suddenly, it came that IP addresses are in short supply nowadays. Yeah. So you see, the idea of what is big is changing. This is why we have to think about this ahead of time. So I'll end this lecture with one small example of what else you can do. There's a guided self-scheduling. There are, of course, many possibilities to do scheduling in a different way. But this is a simple one. So the thing is, the chunk size does not need to always stay the same. But we can also change the chunk size. Now it's, of course, the question, how would we do this? Many possibilities. Here comes a simple one. Or the simple idea is that processes or chunks that start later get less work. So if you arrive late on the construction site, you have to do less, okay? Than the ones who are already there, yeah? And when you finish your work, the new amount of work that you get is smaller than the work that you get previously, because you start your work when others are still in the work, are still working. Now, the way this is done in this particular algorithm, using the number of work items, here again the number of processes, and R is the number of work items assigned. Not yet assigned. So obviously at start this would be n, because there are n work items that are not assigned. And then there is k min, which is the minimal chunk size. Now we use, Now we use the following very simple way of assigning work to the next idle worker. So the next idle worker gets the roof, so this is a roof operation, yeah, so divide R by P, yes. Work items, so this is the chunk size. Of course, only if this R by P is smaller, is larger than the minimal chunk size, and if we arrive at the minimal chunk size, then it gets k-min otherwise. Okay, I guess I explained this by an example, what it means. Example, so say we have 100 work items and we have 5 processors. And say we have a k-min of 1. Let's have a table. So there is the remaining work to be done, which is called R. Then there is the process that gets something assigned, and then there is the number of assigned items. So according to this thing here, starting with R equal to N, the first process, or R equal to N. R equal to N means 100, 100 items have to be processed, yeah? So the process number 1 gets R divided by P, so 100 divided by 5 is 20, yeah? It gets 20 processes, 20 work items. So, which means that there are 80 left. So comes the second process. The second process gets 80 divided by 5. 80 divided by 5 is, oh my God, 16? Yeah, right, you're right. So this is 16. So it gets 16 work items. Then the third process is coming. So they stand in a row, come to the boss. So the boss gives the first guy 20 work items because he has the most time to do the work. Then the next one, yeah, starts the work later, so it's less work to do. Yeah, and then number 3. So now we've taken 16 out of this. This is 64. 64. We cannot divide by 5. The next thing we can divide by 5 is 65. Yeah, and because we have the roof operation, this would then be 13. So we'll take off 13, and then we take 13 off of this, and then we have 51. So 51, now there's this process number 4. Process number 4. So we divide, this is apparently 11, right? So because we have 55, yeah? So, okay, we deduce 11, so which, running out of time, yeah? Which would be, no, we have process number 5. So 40 divided by 5 is, I believe, 8, right? So this leaves us with 32. 32 divided by 5. This is the next one is 35. So that would be 7. So by the way, which process is this? Which process gets 7 assignments? Why would it be 1? Yes, so now you think that 1 comes back first. We don't know whether 1 comes back first because 1 got the biggest chunk. It started earlier and gets the biggest chunk. Yes? So this is the idea. You know, we want to keep them busy, right? So now we don't know who is coming back first, right? So it's the next one. We don't know. The exercise is to equally distribute work. Yeah? So the first one started first, but has more work. Yeah? So this is, we don't know. It's just the next one coming back. And 32, so we take the 25. Okay, that's something I know. It's just the next. It's 5. Then we go to 20. 20 divided by will still be just the next one. By 5 will be 4, giving us 16. 16, the next of 16 again is 4. Then gets 12. Next, so the next is 15, so it will be 3. And this gives us 9. The next coming here, this will be 2. 2 will be 7. Next, so 7 again is 2, then we end up with 5. The next one will be 1. And then we have 4, next 1. Okay, now you get it, right? So there would be 3, 2, 1, right? Zip. Okay. So this is how this thing here works. So how much, I'll stop the recording. How much break do you need?